So let's talk about this one. So again, I'm going to first present what's traditionally done in dimensional analysis, right? And this is how I did it the first year that I taught. Okay, so I need to do some dimensional analysis. So I'm going to give them like 4 or 5 problems here, and these are just some sample problems to make sure they can convert from liters to kilometer or kiloliters. And you know, the better version of this, I guess, is like, first of all, like, why would you need to convert? If you have 40 milliliters, is there any reason why I would put it in liters? I don't know, it's a bit of a stretch, right? Like 40 milliliters, I can actually see that in a graduated cylinder. 0.04 liters, I'm like, okay, so there's not really a reason for students to do these, besides as kind of a mental exercise. It's almost like doing Sudoku, right? Like it's an individual problem that you're just doing because, oh, I guess it's fun, you know, to write out the dimensional analysis across. Okay, a little bit better is a runner completed a 5-mile run. That's nice. That I know what exactly that means, 5 miles, okay? And then I want to convert to yards. I guess that's kind of cool, right? You can put it in yards and present that. But again, this is high activation energy when I'm looking at it. High activation energy for the students. They've really got to get through a lot and motivate themselves to do this, right? And same with molar conversions. Like, okay, why in the world do I need moles if I have 2.35 grams? Like, I can measure 2.35 grams of moles. Why do I even want that? And of course you can tell them, oh, it's going to come up in stoichiometry. That's true. But then you're like, stoichiometry, what's stoichiometry? Well, stoichiometry is this, and you're getting too far ahead of yourself. So you want something that's immediate impact that students can relate to. All right, so here's how I present this. And I'll start off with the video. So basically, the Admiral will explain it. And he's in the he was in the hospital at this point, so there's no video, but there's a sound recording, and there are some pictures, and he'll explain why he has this stupid looking eye patch on.
Dear ACT specialists, I hope you have successfully mastered the 5 main types of chemical reactions. It will be very important that you can apply these reactions in future scenarios. In recent news, we have found that the Batarian scientist who developed the New Delhi disease goes by the name of Balak Totarian. He is the chief scientist of the Batarian team and now wanted by the Alliance military. I personally encountered Balak trying to escape Jupiter's orbit. When I boarded his ship, we got into a scuffle, and he took out my right eye. I managed to knock out 2 of Balak's 4 eyes, so it ended up pretty even. Needless to say, if I see him again, I will take him out and avenge those innocents whom he has injured. I have 2 main missions for you starting today. The first mission requires you to explore current potential habitable exoplanets. As the human population increases exponentially, we need to expand our colonies to other planets in the solar system. I need your teams to calculate the distances these planets are from Earth and the time that it would take us to travel there. Next, I want you to resupply our outpost on the moon. I will put you in touch with our chief scientist and resource manager on the moon, Tamio Yue. As a child, Tamio's Asari parents abandoned her on the moon. Lucky for us, Tamio was adopted by 2 human parents and showed incredible intelligence at an early age. She is now one of humanity's most valuable scientists. It is critical that we get chemicals to the moon. The moon has been one of our most important defense outposts ever since we colonized it in 2114. With rumors spreading that the Batarians have formed an alliance with Krogan and Borcha races, keeping the moon well supplied will be vital to our survival. May the sun shine brightly upon you all. Baroda out.
Okay, so that's kind of how I start the unit, right? So again, I'm just trying to build up. There's no words about dimensional analysis. There's nothing about molar conversions, because I don't really care whether students know those terms initially. Okay? So after that introduction, we start brainstorming, and I say, okay, let's not start with exoplanets first, because those are really far. Let's start with something a little bit closer to home. Let's travel to Mars. And we have a perfect example. And again, like I said, anytime I can get this rover on the screen anywhere, like that gets me excited, because I'm just thinking, oh yes, the Curiosity rover. It's so awesome. I wonder what it's doing, if it's like lasering something, you know, right now. But it's just like a scientific lab in one place. It's so awesome, and the kids love it. So I'm thinking, okay, we need to travel to Mars, but unfortunately, 200 years in the future, the United States government is still using English units. So that sucks, right? Everyone else in the world is using meters, and they know exactly what 55 trillion meters is, and I'm just like, what's 55 trillion meters? So unfortunately, what we're going to have to do is we're going to have to convert this to miles, right? Because I want to know approximately, and I want to have a judgment, and I want to be able to compare like the distance from here to the moon. You know, how many times greater is Mars' distance? Okay, so that's how I kind of sneak that in there. An important dimensional analysis problem for them to do. And then I have to break it down, right? And then I teach in a more traditional method where, okay, like obviously I might need to get from meters to kilometers first because I want to give them the conversion from kilometers to miles. We're going to need to learn the metric scale. We're going to need to learn how to do conversions like that and throughout. One they like is how heavy the Curiosity rover is. They don't really have a sense. They want to know like how big is it? Is it like this massive machine? Because you can't really tell in the picture, right? Because it's on Mars. It's like, what are you referencing that with? Like the mountain in the back? Like, oh yeah, I've seen that mountain before on the satellite. But so they would ask, you know, is it heavier than a car? All right, and I say, oh, well, the Honda Civic weighs about, I don't know, like 1,200 kilograms or something like that. And like 1,200 kilograms, like, is that heavier than that? All right, so now they've got to do this comparison and see which one is heavier. So basically, anytime they ask a question, I just kind of give them another problem. Like, oh, is this heavier than this? Oh, I don't know, like, here's the weight of this. And they're like, can't you just give it to me in pounds? I'm like, I don't know, I only know the metric unit now, so I kind of forget pounds. So this is a kind of immersive way for students to think about it, okay? Now, I finished the lesson, right, and I'm ready to give them some homework because I want them to go home and I want them to practice doing some conversions, all right? So what I could do is I could probably go back to this kind of work if I wanted to. And I think they're a little bit more engaged than they otherwise would have been because, you know, in class they know it's important. They see how it's relevant. But that gets me maybe the activation energy a little bit lower. But it's not as low as I want it to be so that every student is. So I've got to take it one step further. So how do I take it one step further? I say, okay, did you know that there are these planets out there that's detected by the Kepler satellite that we think might have life on them because they have liquid water, right? So the Kepler satellite, there was a recent article on the New York Times. Anyone see that article where the Kepler satellite? That was an awesome article where they showed all the planets that Kepler has discovered and all the planets that orbited it. It was this great visual. It was really awesome. But you can bring that up here. There's a great video of Kepler 22b on YouTube. Just search Kepler 22b, and you'll get this awesome video about how Kepler might have life. And it could be an ocean planet. It could be a rocky planet. It's this many light years away. How could we travel to there? It's a great video that can engage students. But I tell students, look, we want to travel to these exoplanets. So how far is 22 light years? Okay? Is that far? Is that close? What is a light year? And so we engage in these conversations about things that they're actually curious about. They want to know how far that place is. They want to know how much time it would take to get there. They want to know, I don't know, they might not want to know how many apples you need to feed you on the trip, but I just kind of throw that in there. You need some source of food, right? So we're just going to throw it out there. And that water might be an overestimation because at the time I forgot, you know, they just recycle the water on the space system, right? You just kind of pee somewhere and then they recycle that water and then, you know, you got it all back. So it's probably a lot less than that. But it gives them a sense and something valuable and a reason to do these problems, I think. And this is probably about as close to Call of Duty I'll get, right? Like, you know, I'm a little strapped here on cash, so maybe if I had a little bit more money, I could write a program or something that would be a little bit more engaging, but like this is the extent of what I've got right now. Okay, any questions on this? So now hopefully they've got a good grasp of dimensional analysis, and I'm ready to do molar conversions, right? So let's say they figure out how far those exoplanets are. They've learned a little bit about those exoplanets and why they might have life because, you know, they're at the perfect distance, the Goldilocks distance from the sun. And now I've found them with this mission right here from this is an English teacher at my school.
Greetings, ACT specialists. As you may already know, we have lost our outpost on Saturn's moon Titan, and the situation looks bleak. Unless we do put all of our efforts into helping Tamiyo Yue restock materials on the moon, Earth might become the next war zone. Although I, commander of the SS Sherwood 106, have been a top English teacher for many years, in these dire circumstances, I feel the need to help humanity and take the charge of facilitating transportation of important chemicals between the Earth and the moon. On the moon, we need some highly combustible gases in order to help protect the inhabitants here. In addition, from the moon, we can serve as a transport hub to restock supplies and send them to Mars. Now, our first line of defense between alien attacks and the Earth. I forwarded Commander King a list of gases and the amounts we need. The difficulty, however, is that because we need to stock these transport ships with many different supplies, we can only give you a limited amount of space to send these gases. You have been assigned 4 equally sized 1,386 liter containers to store these gases. I know it's not much space, but it's all we can give you for now. If we do not receive these gases, I'm afraid we'll have a tough time defending Mars from the onslaught of the Batarian, Fortune, and Krogan alliance. I expect to hear back from you in the form of a letter explaining your reasoning for sending the materials that you did, along with a set of calculations which show you really thought this through. Again, I appreciate all that your team is doing for the Alliance. Without you all, the Earth would have been already run over by the New Delhi disease. Onward and upward. Sherwood out.
So everyone has a little cheesy quote, ending line, that they throw in there just to give themselves a little more character. But this was a collaboration with an English teacher, and students actually wrote kind of an essay justifying why they sent their gases. So there's a little bit of collaboration with English there, because I was thinking, when we really do things, there's always a deliverable of some sort. It's either a presentation on a job or a letter you're writing to someone explaining your reasoning. So I kind of just wanted to throw it in there to make this a little bit more authentic. But okay, let's take a look at the chemistry here. So how's this different than what we looked at before where you're converting things? So a little again, you have to use your imagination a little bit, because if we were real scientists, right, nobody would kind of give you these random units of molecules. Like, no, this is in molecules, that's in moles, that's in grams. So we know we want them to be able to convert from all of these things to different areas of the mole kind of chart here. So how I got around that is that I said, look, this guy's an English teacher, you got to forgive him for not knowing his units very well. So he just kind of put everything together. So I put the blame on them, and then they can go to him, their junior English teacher, and be like, you don't know the units? Like, what? God, Commander Sherwood, you're killing me here. All right. So now what they have to do, the question is, I don't really tell them what they need to convert it to, right? I say, okay, I need to know how much space these would take up on a spaceship. Like, I want to send this to the moon. How much space would they take up? So they're thinking, okay, like I got molecules. Well, how much space does a molecule take? How much space does a gram take? Okay. And now suddenly they see, oh, I need some way to convert this. I need some way to convert this. So how am I going to do it? And that's when I jump in and say, oh, you guys need some help? Good. Here's how we're going to do this, all right? And that's when I jump in. And so I really try to make them feel like there's a need for them to learn the content. I try to make them feel like there's a problem that they want to solve, but they can't unless they have some of these tools. So then traditionally I would model maybe 3 or 4 of these to show them how to kind of use the chart and so forth to the molar conversion, all right? So then we can calculate total how much space do we need on this spaceship. Okay. Now I want them to do some homework because I want them to practice. I know they haven't gotten it all down yet. So I've got to think of another situation that would make sense to them. And he kind of presented that in his video. And that's the fact that we have a limited number of space. Okay, so he said there are 4 containers of 1,386 liters, and that's represented by the graph paper. So the reason it's 1,386 is because this graph paper has 1,386 squares. Okay, it was just convenient for me. And so I said, this is your container, and you've got to fit as many of these things on there as you can. Okay. This is an engineering problem, right? Like, how can we fit things onto a spaceship, all right? So here's your engineering portion right in there. How much can we put on? Now, first thing, obviously, they're going to realize, oh, I've got grams. Like, that's not volume. I'm going to need to convert them. Okay, so the first thing they do is they convert everything to the volume. That's kind of their homework there. Now, I explained to them, each of these gases are worth a certain number of points. So if you send this to Commander Sherwood, you're going to get 90 points for this one, all right, for your team, because you sent that to him. So however many things you fit in, the more you fit in, obviously, the more points you earn. Okay? And so now you got this engineering problem. For example, let's say I want to fit that H2N, and I'm trying to do this problem, so I give them a lot of scrap paper. Oh, sorry. And they might, I don't know if this is 10 by 10, but let's say it is, and they could draw this out as H2, and this is 100 liters of space, where each block is a liter, right? Okay, and if they do that, they mark down on their sheet that they've earned 25 points from Commander Sherwood, and so forth. And they try to fill up as much as they can without going over, because you can't go over. You can't go over in terms of gases. They're just not enough space. So look at this chart and tell me which is the best deal, I guess. Which one is the best gas to definitely put on the ship? What's the first thing you want to put on that's worth, I guess, the most? Just plain.
NH3.
Which one?
NH3?
Yeah, NH3, right? And why is it NH3?
Volume points, it's a ratio of 1 to 1.
Right, so you're telling me it's the highest point per volume ratio, right?
Correct.
Which one do you think students would try to put on?
The 500.
This one right here, right? Because they see, oh my God, 90 points? Yes, that's great, okay? And so I think 80% of my students will try to always have this one on. And if you have this one on, that's wrong. That's completely wrong. That's the worst ratio I think there is on the chart. There might be one or two worse, okay? But that's taking up so much space for so little points. And so they come in and they're like, oh, I got 300 points. I think that's the best one. And then there's some kid who's figured it out, and he's got 350 points. And everyone's like, how'd I get 350 points? Right? And he starts explaining. He says, he doesn't put it in the words you do, because you're thinking at a little bit of higher level, and my students aren't there yet. But he's saying, well, it's not about points. It's about a lot of points and a little bit of volume, right? It's about a lot of points and a little bit of volume, and that's how they talk to me about it. And then we can formalize what's a ratio. What is a ratio? Why is the ratio important? And the great thing about this is because I think this is a skill they need. It's a skill they're missing very much in science. Like what this tells me is if they went to go to a grocery store and they see, okay, that one's 250, that one's 230, they're just going to choose the 231 and think it's a better deal. If they're showing me the same thing on here. But once they've gotten this one, think about the application for this. How many things in this world are ratios in engineering, in science? And how important is that? And for them to be able to develop, for a student to develop a grasp of that, even at a fundamental level, that's so powerful. And for him to be able to, or her to be able to share that with the class and say, here's how I got this. It's the ratio, guys. It's the ratio between points and meters. One last thing I want to emphasize for this is how did I think of this, right? I wouldn't have ever thought of this if my only goal was for students to be able to do dimensional analysis and molar conversions. I would have never thought of this scenario because these are perfect problems if all I care about is students can do dimensional analysis and molar conversions. They're perfect. If students can do these, they're going to do awesome on the test, right? But I want to challenge them a little bit more. I want to create a problem that's realistic, that's authentic. And if I want to do that, like, sending a shipment to Mars, I think that's a fairly, that's a fairly reasonable and realistic kind of thing. Then that's when all of the thinking comes in. Like, that's when you need all these ratios and things like that. Sorry, I'm in a little trouble here, but that's when it comes in. So the argument I'm making is that unless we provide authentic situations for students to solve, we're never going to, it's tough to get those STEM skills in. Yes?
I would move it all the way up until the graph.
The graph.
Not along the graph.
Sure. Yeah, so what I'm saying is I'm trying to fit all of these things. I'm trying to fit as many of these things onto the graph here. The graph is my visual for the container. Each one of these is 1 liter of space. So if I want 100 liters, they can plot out like a 10 by 10 thing and put that H2 in there. And if they do that, they get 25 points. Now, if they want to put more things on, they want to put as many of these on as they can to earn the maximum number of points. But there are certain ones that are better than others. They're not going to be able to fit them all. They might be able to fit 6 or 7. And so they're trying to earn the lowest points. So
They're not like graphing per se, they're just putting their
yeah, sorry, it's not really a graph. It's more of a visual representation of each of the containers. Yeah, sorry about that. Yeah, sorry about that. Yeah, sorry if that wasn't clear. But thank you for clarifying. Yeah, it's just a visual representation of the space that they're taking, just to help them along. I think it makes it a little bit more engaging. Yes.
Incorporating the gas laws at this point, or not?
So, good question. Well, when I get to gas laws, I revisit this, but I say, guys, there's a way we could fit all of these on the spaceship. And that's if we increase the pressure, or if we take down the temperature. And so we come back to this, and now they're suddenly realizing, oh my God, we could have done it if we only knew this before. Like, we could have sent more gases to Commander Sherwood. Like, I'm so sorry, Commander Sherwood. I didn't know that at the time. So it's good that we can revisit, but I like your thought process there. That's a perfect, further application of this. We can really nail down. Yeah. Okay, so that's one thing that my students really